Solving general chemistry problems, reaction kinetics. I'd like to return to the reaction profiles of the graphs of reaction coordinate versus potential energy in order to incorporate some of these additional ideas we've brought up since then, things like reaction mechanisms and catalysis. Let's explore this in the context of some problems we might encounter on an exam in general chemistry. A certain reaction has an activation energy of 40 kilojoules per mole and an enthalpy of reaction of minus 30 kilojoules per mole. Draw a reaction profile for this process. And what is the activation energy for the reverse reaction? Recall that a reaction profile involves following the change in potential energy as the system moves from reactants through its transition state and onto products. It is a graph with energy along the y-axis and reaction coordinate along the x-axis. The reaction coordinate provides a narrow focus on the lowest energy path through the complexity of the molecular interaction region that is a chemical reaction. The reality is certainly more complex and involves many more dimensions of motion, other vibrations and rotations, for instance. But this simplified picture still gives us a useful perspective with which to analyze chemical reactions and develop a more expert sense of what is involved. These graphs seldom use any absolute energy values. It's more about the relative differences between certain points on the graph. Also, some people will prepare these graphs in terms of enthalpy changes, some in terms of internal energy and some in terms of Gibbs energy. The reaction concepts we can glean are all the same, it's just a matter of choice. But that's why I'm graphing it just in terms of the general idea of energy. So how do we create a graph based on this data? Activation energy is the energy required to mount a barrier from the assumed starting point. There must always be a barrier between reactants and products. If not, the system would immediately slide into the lower energy configuration, and you could never have a bottle of reactants. So reactants lead uphill to the transition state. The energy to get there is the activation energy. According to the problem, the barrier height is 40 kilojoules per mole. The enthalpy of reaction is the difference between the start and end of the reaction. The difference between the reactants and the products, hence from the transition state, the reactants descends to a point that is, according to the problem, 30 kilojoules per mole lower than the reactants. This is the reaction profile for the reaction described. But reactions can operate in reverse too. What were once products can become reactants. The barrier in the reverse direction is the activation energy for the reverse reaction. Here is that activation energy. Note that its value is readily seen to be the sum of the other two values, 40 plus 30 or 70 kilojoules per mole. It is positive because it is measured from the products, behaving as if they were reactants. Activation energy is always positive. Energy must go into the system to get it to react. Here's another problem. Here is a generalized two-step reaction scheme. The first step establishes a rapid equilibrium, while the second step is the slow rate-limiting step. Draw a reaction profile to describe this. We again set up the graph of energy versus reaction coordinate. The first step encounters what will prove to be a small barrier, small because we are told it is a fast reaction, and it falls down into a small energy well. This is where the species C is found. Motion back and forth across this barrier establishes the equilibrium between C on one side and A and B on the other. Step 2 reacts C with another reactant D, but this reaction must have a larger barrier because we are told it is the slow rate-limiting reaction. Beyond this second barrier, the energy must descend below the starting point, the reactants, because we are told the reaction is overall exothermic. The energy well in the middle identifies the reactive intermediate C. This shallow well is what will typify a reaction intermediate. The two barrier peaks identify two transition states. The largest barrier is associated with the rate-limiting step, since with the largest activation energy, it will react the slowest. Now here's another. This next problem is almost identical. Can you catch the one-word difference? I'll pause and I'll let you read this through a little bit. How is it different from the last question? Only one word has changed. Now, did you catch that I only changed the exothermic to endothermic? So how does that change the graph? Well, the first step is the same. However, the second step needs to end at a level above the starting point. The reaction enthalpy is an increase. It is positive. This change identifies an endothermic reaction. The other points characterizing the reactive intermediate and the transition state are the same. Here's another slight variation. This is a similar two-step reaction mechanism. This time, however, the first reaction is identified as being the slow one and the second is fast. Remember that we will interpret fast and slow as arising from the relative size of the barrier the reaction must cross over. Here's the same graph on which we will sketch this reaction's changes in energy. The first reaction is slow and rises to a high energy. It takes a lot of kinetic energy to cross this barrier, and few there be that find it. Hence, the reaction is slow. Once the reaction crosses this barrier, it slides down but passes through a small energy well where the reaction intermediate C side that resides. But in falling from that high transition state, it has acquired more than enough energy to cross the next barrier and move on to products. Now remember that the real chemical reaction involves many more degrees of freedom than suggested by simply following the reaction coordinate. That kinetic energy may not be in the right bond, or the collision orientation may be off, and it's not quite as simple as the reaction roaring past the intermediate and onto products. But even if the energy was all thermalized and randomized at the barrier to go on to products, it's much less than that to go back to reactants. The second reaction step is fast compared to the first step. The reaction intermediate is again found at the energy well, and the transition states are at the peaks. The exothermicity is shown by the products ending up at a lower energy than the reactants. Now here's a summary of some general ideas about these graphs. When asked to create or interpret a reaction energy profile, the main points to observe are: 1. Transition states are found at peaks. 2. Reactive intermediates are found in wells. 3. The difference in the beginning and end of the plot, the difference between reactants and products, is the reaction enthalpy, or internal energy or Gibbs energy, depending upon how the graph is created. A product energy level below that of the reactants indicates an exothermic reaction. A product energy level higher than that of the reactants indicates an endothermic reaction. The energy difference between the reactants and the highest transition state is the activation energy for the forward reaction. The energy difference between the products and the highest transition state is the activation energy for the reverse reaction. Now, one additional feature needs to be included in these reaction profiles, and that is how we treat the introduction of catalysts. We want to imagine a generalized endothermic reaction with a large activation energy barrier so that the reaction is comparatively slow. The mechanism is the simple one-step process of A and B colliding to form C. Such a reaction profile might look something like this: a large barrier for an endothermic reaction. Consider now the possibility of introducing a catalyst. It reacts to produce an intermediate that goes on to complete the reaction. The end result is the same. A and B have been consumed and turned into C. However, the two-step mechanism has A reacting with the catalyst to form an intermediate, which in turn reacts with B to produce the catalyst back along with C. A reaction profile could look something like this, where we now have a two-step process. There are two transition states, but both are substantially lower than the original. The reaction rate will increase. Note that you will sometimes hear the language regarding catalysts to suggest that they lower the activation barrier for the reaction. Well, this is not quite right. Instead, they introduce a whole new reaction pathway, which includes barriers that are smaller than those along the original path. In this example, A and B collide to form a transition state leading to C. In the catalyzed process, we do not even consider A and B colliding. A and D collide to make E, and then E and B collide to make C, as well as D back. It is a wholly different chemical reaction pathway. Now, just to complete the question, to make sure you realize this, D is the catalyst and E is the reactive intermediate.